How about you? Do you fish? We'll have to talk. Okay. Okay, so a few more slides. I don't know if we're going to get through this chapter. We might. We'll see. But like 6:20 or so is we're at, or you know what I mean, 8:20. We're out of here. Okay, so aerosols we kind of talked about a little bit. Basically, aerosols are stuff that are suspended in the air. I guess that's why they call them aerosols. And they can be, but they're not gas. So that leaves solid and liquid. Okay, so that's aerosols. So aerosols can come from natural reasons and they can come from man-made reasons. Okay, but what they have in common, whether they're natural, Mother Nature, or man put the aerosols in the air, is that they tend to kind of give a cloudy effect, so they limit visibility. If you think about it, and we'll talk more about what fog is, but what do you think fog is? What is fog? Aerosol. It is an aerosol, exactly. A fog is, sometimes they say a cloud on the ground. That's what fog is. And so what a cloud is milky white. A cloud is only milky white because water is liquid. Little liquid water droplets up there to make that milky white. And they kind of makes that sort of opaque look. Light hits the liquid water particles in the cloud and it internally bounces around and it looks milky white. Yep, exactly. So I added this. I was in my office and I just couldn't resist, you know. Because the last thing about aerosols is that kind of like you see Pigpen kind of have the dust behind him, okay? Aerosols are more abundant, particulate and liquid aerosols near the Earth's surface. Because here in a minute we're going to kind of break out of the Earth's surface, okay, this what we call troposphere, and we're going to kind of talk about layers of the Earth's atmosphere. So the farther you go up, the less you're going to find particulates. It makes sense. The air's cleaner up there, right? Okay. So if you look real closely, and I'll go ahead and dim the lights again, actually you kind of see fuzziness, okay? So it looks like maybe sandstorm, okay? But some of that fuzziness is due to pollution, okay? So, and I don't know where the line is, okay, but I'll just kind of, this says dust storm, this says air pollution. Okay, this is like a satellite image looking down, okay? So this would be natural aerosols, and this would be man-made. And I don't know, did you run into, on your slides, did I use the term anthropogenic?
Yes.
Okay, good. Okay, so on that carbon dioxide slide, when I said anthropogenic, that means man-made. Like if you study humans, you're an anthropologist sort of thing. Okay. So I don't know. So one thing that particulates can do is when the sun is low on the horizon at sunset or sunrise, we get our pretty colors. Okay, that's when the sun is the prettiest. And we'll talk more about Rayleigh scattering. Okay, but basically that's why the skies are blue, and that a crazy amount of Rayleigh scattering when the sun is low on the horizon will kind of remove the short wavelengths of colors, and that's why you get those long reds and oranges. Okay, but the thing is, if you have particulates in the Earth's atmosphere, you can get it. They can have the sun's light can kind of bounce around extra special. My thing, have you guys ever noticed around here during harvest time in the fall that when the sun is low on the horizon during harvest time, I think those are the most beautiful sunrises and sunsets. And I really think, and I haven't read this, but I think it's potentially an effect of kind of the dust that's thrown up during harvest time. Okay. So aerosols. That was all about aerosols. So the three variable gases, what are the three variable gases?
CO2, oxygen, and...
Not oxygen. CO2, though.
Night.
Nope.
Ozone.
Ozone is, yeah, CO2, ozone. And what was the first one we didn't talk about yet? It's very important to weather, though. When it rains.
Water vapor.
Water, exactly, water vapor. Those are your three, yep. Nitrogen's pretty steady, oxygen's pretty steady. Okay, ozone varies, though. So I mentioned there's good ozone and bad ozone. The good ozone is the ozone. I'm going to talk a little bit about ozone depletion. I'm going to talk about the ozone layer here in a minute. Okay, so good ozone, the reason it's good is that one of the energies that from the sun, ultraviolet radiation, can actually cause, what do you call it, mutant stuff. Our cells can mutate. Yeah, our cells can mutate, like mutagens. And of course, I'm alluding to cancer. So too much ultraviolet radiation from the sun, and that's a bad thing for us. So the presence of O3, okay, you're familiar with oxygen. The symbol for oxygen is O. Okay, usually oxygen runs around as two O's together. We saw it in the video a minute ago. O2, okay, that's regular oxygen. O3 is ozone, just three oxygens stuck together. Okay, and it happens to be, the good ozone layer is in a layer we call the stratosphere. Okay, that might be coming up. But now,
clouds are.
What's that?
That's where most of the clouds are. As well.
There are some special clouds in the stratosphere, but most clouds are in the troposphere. But there are some very cool stratospheric clouds. Yep. So bad ozone, I went ahead and brought in, and you have it on your handout, I think, but if you've ever seen this sign, like when you're near a big city, driving down the freeway, okay, ozone alert. So clear in Unit 5, when we talk about pollution, we'll talk more about this bad ozone. Again, it's O3, okay? Have you ever, like had an electrical something kind of like blow up on you, and you smelled something hot? Hot electrical stuff is O3, ozone. You're smelling ozone.
It stings.
Yeah, it's not a good thing. It stinks, and I'm like, I don't like electricity, so I'm like, ah.
I got a question.
Yes.
I've got a buddy who moved to Chicago, and then he came back here, and like when he got back, his allergies were really going crazy. Is that maybe because he was so used to being around all the pollution, or?
I don't
Also,
know.
maybe because if he was in like the Chicago metropolitan area, there's
Downtown,
less
yeah.
pollen as well.
Yeah.
Because we have, to be quite frank, we have a lot of plants, and Chicago doesn't.
Yeah, I think that might be more.
That's different.
Yeah, I think.
But I think it was. Is it pollen for both seasons, for both fall and winter?
It can be,
I
especially
think
if
it was
ragweed
fall.
is fall, because I'm allergic to ragweed, and it's awful.
That makes
And
more
then
sense.
you get a lot of your other stuff in the spring.
I hope he found good things to come back to, not just the allergies he got when he. But yeah. So there
Less
is.
noise pollution.
Yeah. Less noise pollution. But ozone, like if you have asthma, it can aggravate your asthma if you already have breathing issues. So let's talk about the good ozone going away, the notorious hole in the ozone layer. Have you ever heard of the hole in the ozone layer? That's what we're going to talk about here. So let's see, I'm going to write this on the board. I hope this marker works. We're going to talk about layers of the Earth's atmosphere going up, like a sandwich, kind of layers, okay? And if this, that's my version of the geosphere, okay? And here is the atmosphere. And this layer right here, and there's words coming up, maybe you can see it coming up. But this is called the troposphere. Okay, troposphere, that's this. We're walking around the troposphere. It's pretty thin, the troposphere, but we're going to see that the Earth's atmosphere is squished down here, so even though it's thin, it's cut lots of gas particles. Okay, then above the troposphere, we have a thicker layer called the stratosphere. Okay, and then above the stratosphere, we have the mesosphere. These aren't drawn to scale. And above the mesosphere, we have the thermosphere. And it's hard to kind of show above the thermosphere, we have outer space. Okay, and that kind of, let me go ahead and do one more thing that's coming up. I mentioned down here it's the thinnest, but if I were to draw the air particles, each of those dots is an air particle. In fact, let me go ahead and just show a little bit, not to scale, but I'm going to draw lots of air particles here, fewer air particles here, What happens when you climb a mountain with regard to air?
It gets thinner.
It gets thinner. That's what I'm trying to show here. Thinner. That's not really thinner. 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 Okay. I don't know if I did it very well. Did you get the idea? We'll talk about that here in a minute too. But I mention this because here in a minute you're going to see that the O3, what's O3 stand for?
Ozone.
Ozone. The ozone layer, the good ozone layer, is kind of right here, like this says, in the stratosphere. Because I feel like I talked about stratosphere. What is a stratosphere? Okay, it's just a layer of the Earth's atmosphere above the one that we're walking around in. Okay, so I have a kind of a, my background's in chemistry, but I don't really want to, hold that against me. You try not to hold that against me. So I'll show you a little bit how these CFCs stands for. You know what? Anybody know what CFCs stands for?
Fluorofluorocarbons.
Yep, chlorofluorocarbons, exactly. And they used to be used a lot, and I have a slide coming up into how they were used where. You don't have this.
Aerosol cans?
Exactly. They were used as propellants and aerosols. Yep. Just casually. They were also used as puffing agents. Okay. They were also used in solvents, chlorofluorocarbons, because when you're trying to get a solvent, you kind of mix chemicals to get the right solubility. They do well. And refrigeration. Back in the 80s, lots of cars had to be refit as far as, what do you call it when you charge their coolant or whatever? You had to change that out. Okay. So these CFCs interact with O3 in that layer to break it up. And then it can't protect us from incoming ultraviolet radiation from the sun. That's it. So here's kind of a series of slides. Of course, you see your O3. Does that look O3? Okay, and this is supposed to be a CFC, chlorofluorocarbon. Okay, so what can happen then is the sun's energy will break up and release one little Cl from that CFC. Okay, and then that one little Cl will go and attack an O3. Okay. Now, it doesn't do it like intelligently. Just the chemistry is like that's what it wants to do. It's the energy is favored there. Okay. Then you end up with an O2 instead of an O3. And O2 does not protect us from incoming ultraviolet radiation. Okay. And I think the point here is that this Cl can be liberated to do it again. Okay, attack another one. So bottom line is CFCs, which we as a world have said we're going to stop using, okay, since '87, have done pretty well.
So do we know what about the third oxygen atom in the O3 molecule protects us from the UV?
No, I don't think so. I think that's what they, have you ever heard of a radical? I think that's just kind of but that doesn't protect us. Let's see here, I don't know if it says it right here. Oh, here it is. Can you guys see that 100? Okay. The problem is that once you have CFCs running around in the atmosphere, including the stratosphere, where it can get to our good ozone, that stuff is stable for 100 years. Okay, so even though we stop using it, it's still up there. So, but here's the deal. That ozone hole, you're in luck. Because the hole actually favors the poles. And I personally don't visit the South Pole, and actually the Antarctic is the most prevalent pole, although but there is a hole over the Arctic too. So there's a hole over the Antarctic, it's centered over the South Pole, and it's seasonal. Okay, there is one, like I said, over the North Pole. Now these slides kind of step you through, how come there's a hole and how come it's seasonal? And it has to do with those fancy clouds in the stratosphere. Over here, I'm going to draw let's see, I'm going to draw a cumulus cloud. They're fluffy. Okay. I'm going to go ahead, what's the name of a rain cloud? Storm cloud, cumulonimbus. Yep. Let me go ahead and draw a fluffy storm cloud. And I'm going to go ahead and kind of draw it. I don't know if you guys can see this, but this is my cumulonimbus cloud. I'll go ahead and have lightning coming down. Cumulonimbus is abbreviated CB. And so this actually, can you see where I've drawn it? Okay. Just into the stratosphere. But there are these clouds called PSC, polar stratospheric clouds. And they're kind of a flat cloud, and I have a picture coming up. So I'm going to kind of draw them flat. They are not one of your 10 main cloud types, but they're a special cloud. Polar stratospheric clouds. Huh. Let's see if I must have a picture. Blue, let's see if it clicks. This might be my little video. Okay, so the thing about polar stratospheric clouds is they favor the winter time in that hemisphere. So of course, maybe you guys know that the southern hemisphere is having winter when we are having summer, exactly. So the dead of winter for them would be, yeah, July, exactly. So when there are clouds here, here's the catch. When there are clouds there, remember, well, when there are clouds there, the little cloud particles tie up the CFCs so they can't do bad things. So when there are clouds there, there's no ozone depletion. Springtime comes, and it warms up here, and these clouds go away. So when springtime comes and the clouds go away, what happens is that those CFCs that were tied up when the clouds were clouds, when it's cold, when it gets warm, those CFCs go do their bad thing all at once. And what's their bad thing? To take O3 and break it down into O2. And so the hole actually is in the springtime, when the clouds are going away. Summer comes and you figure the depletion, the thrust of the depletion is gone. So it's kind of at that transition, when it's transitioning to warmer time. So I'm going to show you the real data. Okay. Was there any words there you need to know? So this is a figure from your textbook, but if you're like me, I'm like, I don't want to know, 4 years ago. I want to know current. But what I'm going to show you, the current data is the same scale. So what blue means is it means it's depleted. The O3 is depleted in an area. Yeah. Okay. So I hope I have it current. Maybe I don't. This is a figure from your textbook comparing 4 years apart, how large the hole is. So I said spring, so spring for us might be March. Yeah. So March is the 4th month, adds 6 months onto that, and you do get about October or so. Okay. So here and about here is where their springtime is. Those clouds are disappearing. The CFCs are depleting the O3. But it looks like the hole is less than it was in 06. What you're reading? Let's see if this was my real data. The word changes is boom. Okay, so January 12th of 2015, okay, that is the current ozone. And to me, this is what I thought was interesting, where it says season for this year, 2014. Again, they show, this is the size of the hole. Okay, so this is the size of the hole, and this is the minimum O3. So you want the hole to be small, and you want the O3 to be as large as possible. What's that?
It's not that bad.
Yeah. Any questions about that? I have a lot more to add to that. Oh, the Earth's atmosphere. It's a complicated thing. Definitely switching topics. Those little dots that I drew over there, that's what I'm talking about here, okay? Remember, one of the things you're going to record is atmospheric pressure, okay? So pressure is about, is it doing something funky?
The clock is
Yeah,
right
it went
now.
back to normal.
Oh my gosh, that is so creepy. All right, who did that?
Nobody.
Okay. Dang.
That is really
I'm okay with that.
Yeah, now it's not gonna bother me.
Nope, we've been here for just that long. It's really 10:06.
Oh no, nice try. That is strange. So when you climb a mountain, you said the air gets thinner, and so people who like do that sort of thing, what do they need to adjust for?
Oxygen.
The oxygen. Yeah, that was going to be my point exactly. Nitrogen is less up there. Oxygen is less up there, even though it's about 80-20%. You know.
You still have to have the right amount of nitrogen though in your oxygen tank.
Really? Still have to have the right amount of nitrogen in your oxygen tank? Makes sense, I think.
Say what again now?
You have to keep the same amount of nitrogen levels when you go up. Otherwise, because if you have a nitrogen or oxygen imbalance that you're not used to, you'll get stomach cramps if you ever climb high peaks.
You have to keep the ratio
So
the
then when they
same.
scuba dive in those,
You have to go up slowly if you scuba dive because your body has to adjust.
but
to
your
the
mixture
levels.
is not equal.
You have different tanks.
Yeah, your mixture is not equal though.
No, not equal, but it's the same ratio, like that you're used to.
Cool. I don't know. I can't speak to it. Have you done mountain climbing or
I've done scuba diving. I want to go mountain climbing.
both extremes?
It's crazy. Like I went to Colorado, and it is pretty crazy. Like
How you
go
get
there for a couple
affected?
days, and it affected me big time for like the first day.
But then did you adjust after you were there? Yeah.
It's like I've also read that if you want to go to Machu Picchu or in Peru,
Mm-hmm.
that you need to spend the first 3 days just getting acclimated to the weather or to the atmosphere there because it's so different than if you just try and do it right away.
It would not be a good
Can't do
thing.
it.
Interesting. That's cool.
When they climb Mount Everest, they have to go up so many feet, and then they have to go back down, and they have to keep increasing over the amount of days because they can't climb it all at once.
That's interesting. Well, so you baseball players, you baseball fans out there, so Mile High Stadium,
Yeah.
it's got a different sort of,
Coors Field is in Colorado, and it's more of a hitter's ballpark because of
the density's different.
Yeah.
Did you know that?
You can get tickets
The
to
ball
Coors
flies
Field for
different.
$6. I'm not kidding. I did it 4 times in.
What field is, who's,
Coors Field is
Colorado
in
Rockies.
Denver.
Oh.
In Denver.
Oh.
Colorado Rockies.
Oh, Coors Field.
They have a section called the Rock Pile. It's in dead center field. It's real nosebleeds, but you can literally walk up and be like, "Here's $6. Give me a ticket," and you can go and sit and watch the game. It was awesome.
If you watch football games early in the season at Mile High Stadium, people are dogging it because they're not used to it. It's so hot.
That is so cool. I feel like I've been on vacation. So we could what I drew over here is kind of represented here in this box of air. Okay, so the Earth's surface would be down here, and then going up in elevation, the air gets thinner. Literally, there are fewer particles, okay? But one of the things we're going to see about lower part of the atmosphere is that the air is pretty mixed. So it's what we say homogeneous. So,
Can you go back to that last slide, please?
sure.
And 1, 2.
This one?
Thank you.
You're very welcome. So one of the things, you're familiar with like the 3 physical phases of matter? You know, matter can be a gas or a liquid or a solid, and or plasma. But gas that's a solid is, you can't squeeze it down really, and gas that's a liquid you maybe can a little bit, but you really can't compress it. But matter that's a solid, you can't compress it. Matter that's a liquid, you cannot compress it. But when matter is a gas, you can compress it. But, as you guys maybe know, you can compress a gas to the point of making it become a liquid. All right. Okay. So, we're going to be talking more about gas pressure. And I just love picturing gas particles because they have so much motion. You know, a gas particle over here, started out over here tonight, way over there. Okay. So gas particles move a lot. They have a lot of energy because there's energy associated with motion. So it's that motion that creates pressure. So I brought, and sometimes I actually blow these up, so this might wake you guys up. So this obviously is a balloon, and this little plunger will allow gas particles to fill the balloon. Yeah, just stretched it. Okay, and those little gas particles that go in there, ooh, they get pressure against the balloon. I just love thinking about that. Oh, that pressure. Wait a minute, ready. There it goes. That's a good sign. Okay.
You make balloon animals?
What's that?
You make balloon animals?
No, I cannot. I should try. Okay. So we could increase the pressure by putting more gas particles. Another thing we could do, I don't know, it might be tricky, but is to heat up the gas particles. Okay, what happens to the motion if we heat them up? They go faster. Exactly. And if we combine them to the same volume, if you heat them up, they'll have more pressure. This is the way gas particles are. Okay? Let's see. So with density becomes pressure difference. So high pressure down here, low pressure up there. Okay. We'll be talking more about this, and this is a little interesting, but you know the 30.09 inches of mercury, okay? It's adjusted for elevation. So even though if you go up to Colorado or Denver, you know, the pressure's going to be less. When you look at a newscast, they're going to already correct for the elevation. It's kind of an interesting thing. Okay. So here we go. It's kind of a busy slide. Along the y-axis, we have elevation, okay, elevation. And along the x-axis, we have pressure. Okay, so this is saying, and I think you might have a homework question about this. Okay, I'm not going to get through this chapter. There's no way. Because you have a homework question about this. If you want to write HW stands for what? Homework. Yes. You will want to use this figure for homework. So let's do this one together. What if you go up 10 kilometers? What is the pressure? Let's see, 10 kilometers. I'll change my pen to green. This is kilometers, so 10 kilometers. What do you think? What would you estimate it? Yeah, maybe 250, 260, yeah. Okay, so the pressure up here at 6 kilometers, wait, did I do that? Did my eyes get crossed? No, I think I did that right.
You said 10, but you wrote 6.
Oh, okay, thanks, that was my problem. Let's stick with 6 kilometers. So at 6 kilometers, you're running about 250 units are those millibars again. Remember when we looked at that map a little bit ago?
6 would be below 8, not between 8 and below.
Oh, thank
Just
you.
change it to 10.
Oh, that's sneaky. All right.
Just checking if we're all still awake.
Thank you. That's very kind of you. 10 kilometers, final answer. Okay, what about 6 kilometers? We'll change that to purple. Out, and it really is here, right?
350 or so? No, way 500.
Let's see. I know, you have to kind of, so that's 400, 500, 600. Yeah, maybe 480. Yeah. Cool. So what about, let's go about, you think this is sea level? Does that make sense? Oh, good. So what sort of pressure do we have at sea level?
About 1,000.
About 1,000. And actually, 1,000 millibars. Isn't that handy? Yep. What's the next slide? I think that's a good place to stop, because then we'll take a running start at it next week. And we'll knock out the rest of those slides for this chapter. So chapter 1 is not due next week, but it will be due the following week, for sure. And chapter 2, if we get through chapter 2 next week.
So you're gonna have the same atmospheric pressure at sea level as you would at 32 kilometers.
32 kilometers? This is 2,000 kilometers. So you're saying 32 kilometers like up here?
32,000 kilometers.
Oh, sorry, 32. Sorry, 32 kilometers up there. No, at 30, I was reading that wrong, sorry. At 32 kilometers, you're up here. And you're basically right, yeah, you're close to 0 in terms of millibars. So it intersects right here, you bring that down. You know, I can't really bring it down, but you're, yeah.
Fair enough, I see what you're saying.
Yeah. So that's all I have today. So we'll see, if you have any questions, let me know. But that's the plan, man.
9 straight hours. I've never stayed up this long.